So welcome back, everyone. I'm again excited to continue this pharmacometrics series with you. The last time we covered the basics of modeling with introduction to physiologically based pharmacokinetic modeling, that is PBPK, as well as population pharmacokinetic modeling. So I hope that you were able to review those concepts before now. If not, recording was made available on YouTube, so you can also check that out. So today, we are going to be building on that foundation and dive deeper into PBPK modeling. So here is what I have planned for our time together today. First, I am going to be doing a quick recap of compartmental modeling, but this time I am going to be focusing on concepts that will facilitate our understanding of PBPK equations. Then after that, we are going to be walking through how PBPK models are developed, and that is in relation to how to set up the system and what it takes to set up the compound. So finally, we are going to be wrapping up with talking about how and where these PBPK models can be implemented in practice. So with that said, let's get right into the webinar. So let us start with this hypothetical scenario of someone taking a dose of a drug X by mouth. And, we are interested in modeling what happens to drug X inside the body. Now, this basically comes down to two questions. We want to know who and we want to know what. So when I say who, what I mean is who is the biological system that we are talking about. In this case, we are talking about human being, and then the what is about the drug. So what is the nature of the drug we are talking about? So in this case, we are referring to drug X. So first, let us talk about sorry, let me minimize my screen. So first, let us talk about the who. That is the biological system or the human body. Okay. So now in this human body model that I have described here, I have tried to do a best guess of approximating the human body. Although this is not what the human body would look like in real life, but this is an approximation. So the human body here, I've tried to describe it using the gut compartment as well as the blood compartment. So whatever goes into the gut either goes out as a result of the gastric motility here, or it gets absorbed into the blood circulation through this arrow that you are seeing here. And then each of these compartments that you are seeing here have their parameters that describes them. So this is as far as the biological system is concerned. Then the second aspect is the drug that we want to use. So in this case, I said drug X. So when we bring drug X into the picture, then the drug also comes with its own specific parameters that relates to the drug. For example, the absorption rate constant Ka here, or the clearance of the drug, the CLX. So these two parameters are something related to the drug. So if I change drug X to drug Z, for example, then the Ka and the CLX is no longer going to be the same. Then I have to use those values for that new drug. Okay. Now, with this understanding, let us describe the kinetics of drug X using this simple model. So basically, we want to follow the kinetics of X in each of those compartments as it is moving along. So let's start with the gut compartment. So if you focus your eye on the gut compartment for a minute, let's see what is going on here. Okay, so the amount of drug X or X in the gut compartment per time, we can define it by this equation. And the easiest way to visualize this is to think about it like, if you have an empty building and then in the morning, a visitor comes with, let's say, 20 balls. And then when the visitor was leaving in the evening, the visitor left with 12 balls. So if I ask you what would be the amount of balls in the house at that time that we are looking at it, then it's going to be whatever ball was brought in and then whatever balls left. So that's 20 minus 12, which is going to be 8. Basically, when we are describing PBPK model equations, this is the same thing that we are doing, input minus output. So for the gut compartment, our input is what is coming from the dose of the drug. Our output is the loss of the drug as a result of this portion, and then the loss of the drug from the gut into the blood as a result of this part. So although this is the part that we want drug to be lost from the gut to the blood circulation, but maybe we don't want the drug to be lost from the gut, through the excreta outside the body. Okay, so but then the two processes that describes drug loss is this KTR and the Ka. So if we bring that into equation, then the input will be the dose minus the KTR times X gut, that is this portion, and then minus this one, that is Ka times X gut, which is this part. Okay, now, once the drug is now in the blood circulation, then we can also describe the kinetics of drug X in the blood circulation as well. So if we also focus on the blood circulation for a minute, then to describe the equation, we are going to use input minus output. So for the blood circulation, what would be the input is whatever is leaving the gut and coming into the blood circulation through this Ka pathway. Okay, so that is why the input for this equation is Ka times the amount in the gut. And then output is dictated by this clearance X. So we say CLX multiplied by X blood over volume of blood. By now, I know you have noticed that how come I am writing X blood over V blood, which is not the same way that I have written X gut. I didn't say over V gut. The reason is that if you look at this equation, this is dx dt, that is amount of drug in the blood over time. So if you put that in units, that's going to be milligram per hour. So you know that in science, we want the equation on the left and right hand side to be the same. So the unit of absorption rate constant is per hour. That is why I am only using X gut, which is milligram. So if you bring these two together, you will get milligram per hour, which is the same thing as the unit on the left-hand side. Then if you come to this side, because I am using clearance, and clearance is, measured in liter per hour. So I need to use concentration in that case so that the volume of blood, which is in liter, can cancel the liter part of the liter per hour. And then at the end of the day, when you bring all this together, the unit goes back to milligram per hour. So that means that we are ensuring or preserving unit consistency, which is what we call like mass balance. Okay. So again, just to reiterate, on the previous slide, I tried to think about the human body in a very simple way. And as I mentioned, this is very simplistic. So if we want to be more physiologic, I want to describe what is going on in the body better, then, I am starting to think about physiology of the body, which is the whole essence of PBPK modeling. So then we must capture several processes that is going on in the body. So let us try to modify this and see what is going on in a more physiologic way. So if I use this new model, then you can see now that I have the gut compartment, the liver compartment, and several other compartments. So here now, I am trying to be more physiologic. So if you look at it, whatever comes into the gut would leave the gut into the liver through the hepatic portal vein, which is this arrow. And then whatever is in the liver would leave the liver to join the venous blood, which is the inferior vena cava, through the hepatic vein. And then it keeps going on and on like that. So the new diagram that you are seeing here is our best attempt to put physiology in what we are describing. Because if you look at the one on the left-hand side, it doesn't really represent what is going on in the body. But if you look at what is on the right-hand side, at least, even though it is not fully representative, but we are close, okay? So if you look at each of the compartments, we have some specific parameters that you can see, like the KTR, the Q lever, the V arterial. So all these parameters, we call them parameters, and they are parameters specific to the system. So for example, if we are talking about human being now, the Q lever here will represent blood flow to the liver. So the blood flow to the liver for a human being is different from the blood flow to the liver for a rat. It's different from that for a dog. So if I'm building a model for a human being, then I have to make sure that these parameters that I'm using has to be those parameters defined for that of a human being. So I can't use that of any other species. Okay. Now, if we now say drug X is administered, then we want to describe how drug X moves around the body. Okay, so immediately you administer drug X orally, then the drug goes into the gut compartment, right? Now, in the gut compartment, we can use this equation to describe what is going on in the gut compartment. I have shown you this earlier, so I won't talk much about it. Then once the drug leaves the gut compartment, then the drug enters the liver compartment. So here is a description of the liver compartment. So if you look at the liver compartment, focus on the liver and forget about the rest of the organs. So you would see that for the liver, the input is what is coming in from the gut here. Another input is what is coming in from the arterial blood. Then the output is what is going out of the liver through the hepatic vein, or what is being lost from the liver as a result of clearance or metabolism of the drug. So if you put all this together in terms of input minus output, then that will be this plus this, which are the inputs, minus this and this, which are the outputs. So if you translate that into equation, then you are going to have this equation on the slide. We can also do the same for this organ compartment. And remember, I called it organ because we can have several different organs in the body, like we have kidney, we have the spleen, we have several different organs, the brain and things like that. So I'm just lumping all of them together and calling them organs. So for the organ here, if we also focus on the organ, the input will be this arrow from the arterial blood, and then the output is what is going out from the organ back to the venous blood. So if we want to translate that also in terms of equation, then this is the equation we use. Now, the last two that you are seeing here, the same thing for the lung compartment, by the way. So for the lung compartment, this is taking input from the venous blood and then output into the arterial blood. So if you want to describe that, then we can use this equation. Now, the last two compartments here, which is the arterial blood and the venous blood, they are not really an organ that we have in the body. It doesn't really represent, there is no organ in the body that is called the venous blood organ. But the reason why we are using it as a compartment is just to use them as like a distribution hub. So the venous blood here is like a hub where all whatever is flowing out of the organs, here is where everything is collected. And then once everything is collected here, it goes to the lung for oxygenation and then goes back to the arterial blood. You can think about the arterial blood as the heart, where then, after contraction of the heart, the blood is being circulated to different parts of the body again. Okay, so my point is that even though we have this venous blood and arterial blood, they don't really represent a real organ in the body, but we need them to describe the distribution of the drug. And here are the equations that we use in describing them. Okay, so these equations are pretty standard. You can find them in literature if you want to read more about them. So now to build a PBPK model, we would start by gathering biological system parameters that can describe the anatomy and physiology of each of the organs. And some of them, I have mentioned them on the previous slide. For example, the weight of the organ, blood flow, etc. Then once you have that, the next thing you want to find are the properties of the drug. I mentioned some of them also on the previous slide, like absorption rate constant, fraction absorbed, partition coefficient, and so on and so forth. So when you have these two together, then we can combine them using ordinary differential equations to describe the kinetic processes of drug in that biological system that we are interested in studying. So on subsequent slide, I will now talk about each of these components in greater details. So let's start with the system. Now, if we want to build a virtual subject, we must use parameters that are specific to that subject. I mentioned that earlier. If I want to build a model for a human being, then I have to use parameters for human being as a system. If I want to build for a dog, I have to use parameters specific for a dog. For instance, if I want to define the weight of liver, if I'm building for human being, I have to use the weight of human liver. If I'm building for a dog, I have to use the weight of a dog. I mean, the weight of liver of a dog. So you have to make sure you are using the right parameters to set up the system. So for instance, let us assume we are building for a human being, okay? So in this human being model, there are several organs that we want to define. For example, I need to define parameters for the lung, for the heart, for the gut, and so on and so forth. Now, when we say parameters of the system, there are majorly two things that comes to mind. The first thing that you want to know is what are the parameters that define the state of the organ? And when I say state of the organ, it's simply the size of the organ. So that is basically the weight of the organ. So what is the weight of the lung? What is the weight of the heart? What is the weight of the gut? The weight of the kidney, and so on and so forth. But remember that in our PBPK equations that I showed earlier, what we need is concentration in those organs. And for concentration, you need amount over volume of the organ, not the weight of the organ. Because if I give you a liver, for example, it is usually convenient, or we can easily measure the weight. It is not usually easy to translate or use the liver to measure the volume. So what we then do is, if I know the weight, I can use something like density or specific gravity to convert that weight to volume. Then I can now use it in my model. Okay. So the first thing you want to know is the state of the organ, which is the organ size. Then the second thing you want to know is all these arrows, which represent blood flow. So you want to know the blood flow for each and every organ we have in the body. Okay. So I know that by now you've started thinking probably, oh, this is a lot of information. So where do I get them from? Well, I can tell you for free that, we have several information in the literature that you can use and copy these values from. And let me give you this example of a paper from Zakaria et al. So you can see that all these organs have, we have specification for their blood flow. So when I say blood flow, it's the same thing as perfusion. So we have all these values already defined in the literature. Some people have done the studies, they have reported the values. All I need to do is just to take those values and use it in my model. So you can see we have for human, we have for rat. So if I'm using this paper, for example, and I'm building for human being, I have to neglect the one for rat and go for the one for human being. Okay? So now that we have mapped parameters that we need for us to set up the system, let us now look at parameters needed to set up the compound. Now, for the compound-specific parameters, we are going to need some drug-related parameters in order to describe, these four processes of absorption, distribution, metabolism, and elimination. And again, these values are available online. But the tricky part with the compound setup is that there could be situations where this information could be lacking. You can think about it, for example, if you have a new drug and the drug has not been studied in humans before, then you will probably not have a lot of information. Or let's say this drug was approved like recently, maybe 3 or 4, 5 years ago, then not a lot of people must have studied the drug. So you are not going to see as many information as you want at that time. Okay. So in situations where the parameters that you want are not available, then what you can do is that we can use some kind of guided assumptions or equations to predict these values. This is perfectly allowed. Here is an example of what I'm talking about. So in a PBPK project, these are the parameters that you are probably looking for. For example, parameters describing the physicochemical properties of the drug, like molecular weight, dissociation constant, lipophilicity, and so on and so forth. You're also looking for parameters describing the absorption if the drug is oral or intramuscular. So you have those parameters. You can check literature for them. Then you also have parameters describing distribution like fraction unbound or parameters describing metabolism. So all these are parameters related to the drug that you need to build the PBPK model. So once we gather all this information, then we can start describing each of the processes involved in pharmacokinetics. So today, let me start with absorption.
Pharmacometrics is a great opportunity for Africa because it's cutting-edge science, but it does not require any expensive equipment like other sciences. It just requires a computer, maybe internet access. And there's a lot of young minds that are keen to learn and could have a great career in pharmacometrics. All they need is access to learning opportunities and experience.
Studies are important in determining what is the optimum dose to use in the African population. It's important to include the Africans because we can then find novel associations which can be drug targets that can be used to develop new ones.
Now, there are different routes of administration, as I'm sure we are all aware. So let us consider a simple oral absorption for demonstration's sake. Okay. Now, after we swallow a drug, the drug now is in the gut lumen. So from this gut lumen, the drug has to leave the gut lumen and enter into the gut walls. Okay, but we know that usually it's not all the drug in the gut lumen that will cross into the gut wall. So the fraction of drug that leaves the gut lumen into the gut wall, we call it FA, which is fraction absorbed. Okay, now, among those drugs that successfully cross from the lumen into the gut wall, then within the gut wall, there could also be what we call gut metabolism. So as we know, there are some CYP enzymes in the gut walls or even transporters that can either pump out drugs or pump them in, or CYP enzymes that can two things now. A fraction of the drug absorbs into the gut wall. Then among those, a fraction of them also escape the gut metabolism and then gets into the hepatic portal vein. Okay. Now, once these drug escaping gut metabolism are presented into the liver, then the liver also subjects the drug to what we call first pass effect. Now, as a result of the first pass effect, some of the drug are also metabolized and they are lost. So, and that is accounted for by FH. So that is the fraction of the drug that escapes the hepatic metabolism. Okay. So at the end of the day, the fraction of the dose which shows up eventually in the blood circulation is what we refer to as bioavailability. And what that means is that bioavailability is being described by three essential processes: the fraction absorbed, the fraction escaping gut metabolism, and then the fraction escaping hepatic metabolism, which is the first pass effect. Now, we can use this diagram to further understand what is going on here. So as you can see, the drug, this is the lumen. The drug has to first, the first barrier is that the drug has to successfully cross into the gut wall. So not all the drugs will do that most times. So the fraction of the drug that successfully do that is Fa. Then once the drug crosses, some of them are lost to gut metabolism. Okay, then those ones that survived keeps going and then enter the liver. Then in the liver, some of the drug are also being metabolized, which is what we call first pass effect. And then eventually you have the final drugs that escaped these three processes. So the amount of the drug eventually reaching the systemic circulation is a combination of these three processes, as I mentioned earlier. Okay, so I have denoted them in red because these are drug-specific parameters. You know, it is independent of the biological system. So if I change my drug from drug X to drug Y, then I need to define this parameter again because the fraction absorbed for drug A is going to be different from fraction absorbed for drug B. So it is a drug parameter. Now, the equation that we are then going to use is this equation. And take note that in the previous equation that I wrote, I didn't put the bioavailability because I wanted to start simple. So you have to account for bioavailability because it is not everything that is presented to the gut that would eventually make it to the blood circulation. So the F helps us to ensure that only those that escapes these three processes are the ones that enters the blood circulation. Now, because these parameters in red, we need the values for them. And then if you think about it, usually we may not be able to find this information in the literature. Some of the times, sometimes we can find them, sometimes we may not find them. So in situations where you don't find them, then there are established equations that we can use to define them. And some of them are what I'm showing on the slide here. So as you can see here, if you don't know the absorption rate constant of a drug, you can predict it. And how do you predict it? You can use the intestinal radius, you can use the transit time, as well as effective permeability of the drug. Now, effective permeability can be obtained through some experiments, but even if you don't have that value, or if it has not been reported before, there are also equations to predict effective permeability. So you just need to keep digging, and then you will find equations that can answer each of those parameters that you cannot find or you cannot define. Okay, so the same thing for fraction absorbed, fraction escaping gut metabolism, or fraction escaping first pass metabolism. Okay. Now, let us talk about the next process, which is distribution, right? So when we say distribution, distribution simply means distributing the drug to the site of action where the drug needs to act. For instance, if the site of action is in the brain, then I want the drug to get to the brain. That is when the drug can work. So if the drug is able to get to the brain, then we say the drug is being distributed to the brain. Okay, so let me pick one of these organs to demonstrate what I am talking about. So let us look at the kidney closely. Now, drugs are going to be presented to the kidney as a result of this blood flow, this arrow that you are looking at. Now, I want you to think of these arrows like a pipe, right? Now, even though these arrows, this pipe, these blood vessels are passing through the kidney, that does not qualify to say that the drug is distributing into kidney. We only say the drug has distributed into kidney if the drug leaves the capillary space or the blood vessels and then enters into the kidney tissues. That is when we say that, oh, the drug has been distributed into kidney tissues. Okay, so how does the drug leave the blood vessels or the capillary space into the tissues? So we can describe this using two mechanisms or processes. The first one is called the perfusion limited transfer. So this is the blood vessel, okay? So in perfusion limited transfer, the assumption we are making is that the barrier that the drug needs to cross in order to enter the kidney tissues is very porous. Okay, so because the barrier is very porous, is highly permeable, then drug that gets to this region can easily enter into the kidney. Now, what that means is that the amount of drug in the tissue is determined by how much blood, is flowing to that part. So if the blood flow to the kidney is very high, then what that means is that a high amount of drug would be presented at this region. And because we are dealing with perfusion limited transfer, then that automatically means we are going to see a high amount of drug in the kidney tissues. Okay, so that is why we are saying this is perfusion limited. So what determines how much of the drug you see in the kidney tissues is dependent on how much of blood flows to that portion of the tissue. So if the blood flow to the kidney is very small, then what that means is that only small amount of drug would eventually present in the kidney. Okay, so that means the barrier for the transfer of the drug is not this membrane itself, but rather it is the amount of blood flowing to that part, bringing the drug. So, and this can be described using this equation. Now, the second mechanism is called permeability limited transfer. Now, in permeability limited transfer, what we are saying is that it is this permeable membrane that determines how much of the drug we see in the kidney. Okay, so for example, even if blood flow to this tissue is very high, meaning that a high amount of drug is presented here, how much of this drug eventually enters into the kidney is going to be dependent on the permeability through this membrane, not a function of how much of the drug is presented to that site. So when this is what is happening, then we can say that the drug is experiencing permeability limited transfer. Okay, so let me quickly mention here that for perfusion limited transfer, this is usually what we use for small molecules, because small molecules, they have a very small size. They can easily pass through that spaces within the cells. Okay, or drugs that have high permeability, then those kind of drugs can easily enter the kidney. And then if you want to describe the PBPK equation for them, then you have to rely on this kind of equation. So, and you can see that in the equation, you can see Q, which means that how much of the drug gets into that tissue is determined by the blood flow, which is the Q. In the second one, as I have described, how much of the drug goes into the kidney is determined by the permeability of the drug across the surface. So in the equation, that is why we are saying it is a product of permeability of the drug, which is the P, and the surface area through which the drug is permeating into the tissues. So that is SAT. So the product of P and SAT is what replaces the Q that we saw earlier. So it's either you use the previous one or you use this one. Now the question is, in which situations do we use this mechanism? So we use this mechanism usually for drugs that find it difficult to easily do distribution of drug in the brain, even though the drug could be a small molecule, but because of the blood-brain barrier, because the blood-brain barrier is a very tight junction, then it can also experience permeability limited transfer. So it all depends on which part of the body are you considering, and then you can decide on, okay, which mechanism am I going to use in describing that transfer, okay? So now let us now assume that apart from this kidney functioning as an organ, it can also help us in eliminating the drug. That is this arrow here. So we can also clear the drug from the kidney. So all you need to do here then is just to add that portion of renal clearance. So that's why I'm saying, apart from this, if you look at the previous equation here, it is just Q kidney, C artery minus C vein. That's all. But because I am now saying the kidney can eliminate the drug, then you need to add, that loss of a drug as a result of either that renal excretion or metabolism in the kidney. Then we can use this equation to account for that. So in a nutshell, to describe distribution, we first have to decide on the mechanism of transfer of the drug. That's the first thing. Are we using permeability limited or perfusion limited? Then after that, you have to decide this organ I want to model for, is it an eliminating organ or a non-eliminating organ? If it is a non-eliminating organ, then this is the equation you use. If it is an eliminating organ, then you have to account for that elimination using these extra parameters, okay? So again, I have used those. So the Q organ is a system parameter because it is the blood flow to that organ. That doesn't have anything to do with the drug, okay? But when you look at the KTP, the tissue to plasma ratio, this is defined, this is a property of the drug. So for every drug, the KTP changes. For every drug, the blood to plasma ratio changes. So you have to define those. Now, one of the difficult things that we usually encounter in PBPK modeling is what would be the value for this KTP, because the tissue to plasma ratio, which is what I'm calling KTP, it is usually different for every organ. So the KTP for lung is different from the KTP for heart, is different from that for gut, and so on and so forth. So it's a very expensive experiment to do. And in fact, we don't even do it. So that is why you have to rely on equations to predict what this KTP would be. So that is why we have this equation here. Now, there are several equations that have been developed in the past. We have, for example, Rogers and Rollard equation or Pollin and Thale. So you can read up on them. There are a number of them. So, but this one I am showing here is an example from Rogers and Rollard equation. So, and as you can see in this equation as well, you can see that we are defining it based on the drug properties as well as the system properties. So the log P is lipophilicity of the drug, the fraction unbound in plasma, and then the fraction unbound in tissue. So sometimes, again, if we don't have the value for fraction unbound in tissues, then we can also use this equation to predict it. So again, in PBPK modeling, wherever you don't have that value reported for you in the literature, you can devise, equations to get around it. So that's the whole beauty about PBPK modeling. And again, that is one of the reasons why so many people challenge PBPK, because they feel, you are combining a lot of predictions and things like that. So how do we trust, whatever result you are getting at the end of the day from your model? So we can talk about that. If I want to give you confidence in my model, we can talk about that on a separate lecture. But I'm just trying to let you know that all these predictions is what make some people feel skeptical about PBPK, and they would rather do a study instead of doing PBPK. But there are some situations where you just can't do a study. For example, you can't just say you want to study a drug in pregnant women if the drug is not going to benefit the pregnant women. So there are some situations where PBPK is very, very valuable. And I think we mentioned that in our last lecture. Okay, so the last part of the pharmacokinetic process that we want to describe is the metabolism and elimination. And for metabolism and elimination, the important parameter that we want to calculate here is the clearance. Okay, it's as simple as that. And if you ask me, the simplest or the easiest way to get your clearance is just go to the FDA label and then look at the clearance of the drug. If the FDA label says the clearance of the drug is 40 liters per hour, then just use 40 liters per hour in your model equations, and then you are done. So, but this is not what we do in practice when we are building PBPK models. And I will tell you the reason. The reason is that if a drug is metabolized by CYP3A4 and CYP2C9, for example, if what you did is you just pick the value of the total systemic clearance, then you have not really built that details into your PBPK model. You have not defined each of the metabolism pathway. All you just did is you took the overall value of the clearance, you use it in the model, which is acceptable, by the way. But what I'm saying is that you have not really defined which specific enzymes is contributing what, and then, trying to model this. The benefit of doing this is a lot. First, there are some situations where I want to study drug-drug interaction. So if you have not defined the model in such a fine detail, you will not be able to say, okay, I want to know what is the effect of co-administering my drug with a CYP3A4 inhibitor, for example. If you did not define all those things, you will not be able to study this. Another reason why this is, going in detail is very important is that you can have a situation where the drug is not yet used in human beings. So that means you don't have the clearance value in humans yet. But the only thing you have is the studies that have been done during preclinical stage, like the in vitro result and things like that. So we can take those information about the CYP enzymes, and then we can use it to estimate or project what the clearance would be for that drug when human beings use it. So I'm not saying you cannot use the clearance directly, but I am saying that going into such fine details really adds value to PBPK models. So let's now talk about the mechanisms. So there are three primary sites where metabolism and elimination can occur in the body, and that is the gut, the liver, as well as the kidney. Now, one of the early decisions that we want to make in drug development is we want to know at the early stage which enzyme is responsible for the metabolism of our drug, okay? And to answer this question, there are standard in vitro metabolism experiment that is conducted. And here is a few of them. You can do like a microsomal study, or you can do a liver hepatocyte study. I won't go into details of this study. It's something that we can all read upon. It's available in the literature. But the point I want to make here is that there are two important parameters from those studies that you are looking for, and they are the Vmax and the Km, because these are the two parameters that you are going to use to project what the actual clearance of the drug would be through a process that is called scaling, okay? And I will show you this process on the next slide. So let us say you conducted an in vitro experiment using either microsome study or hepatocyte study. So the two important parameters you are looking for are the Vmax and Km. Now, when you get these two information, you do Vmax over Km, then you are going to, so the Vmax over Km is your intrinsic clearance. But don't forget that we did this experiment in vitro. So the value here is your intrinsic clearance in vitro. So, but what I need is the clearance of the drug in human beings. So you can't use the clearance in the test tube or in vitro to be the equation you use. If it is an in vivo study, this is the scaling that we use. So once you scale, then what you now have is, instead of intrinsic clearance in vitro, you have converted it to intrinsic clearance in vivo, okay? So now once you have your intrinsic clearance in vivo, then you can now apply different hepatic models to estimate what the actual clearance would be in human beings. And I am using the well-steered model as an example here. So the hepatic clearance, for example, would then be the blood flow to the liver multiplied by the fraction unbound of the drug times the in vivo clearance, and then you can get the value, what the value for the hepatic clearance should be. So that's what I'm saying, that instead of you going into the literature and looking for this value, you can use these fine details to arrive at that step. I know it's a lot, but there is value in it. And I think I've demonstrated, or I've told you the reason why this could be important. So if there are other mechanisms also for the clearance, you can also add them. And then when you bring all this together, it gives you the total clearance. Now, the fraction unbound incubated is one of the parameters that are difficult to get. And it is also difficult to conduct experiment to determine it. So how do we get that value? There's an equation to predict it. So again, I don't want to sound like a broken record. If there's a parameter that we don't know what the value should be, there is always an equation that have been established before in order to predict what that parameter would be. So really, there is not going to be a situation where, oh, I don't know this parameter, I don't know what to do. No, there is always going to be an equation to predict it if that value has not been reported before. Okay. So finally, we get to the fun part. There are different software that we can use to build PBPK models, but I am going to broadly classify them into two. So the first one, I am going to say they are like any programming language that can solve ordinary differential equations. And examples of those programming languages would include Python, NumMem, Berkeley Madonna, even R. So as long as that programming language can solve ordinary differential equations, then you can use it to write a PBPK model. The second one is we have some graphical user interface platforms that have been developed by companies, or for either they are for profit or open source, to help us in building the PBPK model. So, and these graphical user interface are quite easy to use, because for the first one, you have to write the code. For the second one, they already have the code written under the hood. All you just need to do is change the values, change the parameters, and then you keep doing that, more like a point and click. Okay. So here's an example of ordinary differential equation solver that I have personally used in the past. The program is called Pumas, and it is based on Julia language. Okay, so as you can see here, if you are going through the route of ODE solvers, then you have to write all this equation yourself. For example, if you look at this line 208, I know it's very tiny, but you can see that this is the well-steered lever model. So you define all those equations one after the other. So this is a lot, and you have to have some experience in coding. So that is why this could be a challenge for maybe some researchers who don't have background in coding, which is fine. So that is why, we have the graphical user interface platforms. So in this platform, you are not writing any code. All you are just doing is change values, click, point, click, point, click. As simple as that. But I know a question you can ask is, what is then the advantage of writing the code or using the software? The difference is that if I'm writing the code myself, I can basically define anything I want. I can define anything I want. I can modify the model as I want. But if you are using the graphical user interface, you cannot really define what you want, because, for example, if you look at on this slide, I am showing you a model of human being, a male. So if you want to look at a situation where maybe the liver changes, or some changes that you want to do, there's a limit to what you can change. So that's really the downside of graphical user interface. But again, it's a very good place to start if you are interested in PBPK modeling. And definitely, this is used a lot, and people do publications using this graphical user interface quite often. Okay, so I know we are running out of time, but I wanted to demonstrate PK sim for us, but in the interest of time, I am going to skip this for the next webinar so that we can then look at that together and then get our hands on the software. So the software we are going to use is PKSIM, and then we can look at imatinib as an example in the subsequent webinar. So thank you very much for your time, and if you have any question, I'll be happy to answer them now.
Next month's webinar is on the 28th of May, last Wednesday of the month. You will definitely get invites. You will see the adverts. Please register as you have been doing before and invite others. You can all attest that this is being broken down to the finest units for us all to understand. Please register and get others on board. Let's build together a pool of pharmacometricians in Nigeria. Yes, at this point, I want to say thank you again for joining, and we'll see you next month.